Alright, so having looked at some basic matrix transformations, particular operators in 2 and 3 space that do some interesting things in terms of vector graphics, we want to look more in depth at some more properties of matrix transformations. And basically the main property we want to look at is the composition of matrix transformations. And so given that we have two matrix transformations, and transformation A, T sub A, is going from a domain of N space to a codomain of K space. And the transformation B is going from a domain of K space to a codomain of M space. Okay? If we give these two, then we can create a transformation from N space to M space that's called the composition of transformation B with transformation A, and it's written this way: TB circle TA. And you've seen this notation. We talked about composition of functions. F circle G, right? F of G of X, right? And that's exactly what it is. This TB composed with TA, TB circle TA, is TB of TA of X. And so, right, we're composing the two together. So, for instance, let's let this sort of plane, quote unquote, represent N space, right? And in N space we have a little vector here called X. It's an N tuple, right? It resides in N space. And then over here we'll have our K space. It's a K tuple space, right? So the transformation A, right, goes from N space, right, domain, to K space codomain. So it's going to map, call this transformation A, and we're going to end up with this vector here in K space. And how do we denote that? It's what we call the image of the vector X under this transformation, TA of X, right? And it's found by matrix multiplication. Okay. But then I can go from K space to M space, and I do that by transformation B. And so this is now what? How would we denote the image under transformation B, the vector in M space? It's an M tuple. Well, it's TB of what? What are we inputting? TA of X. And so we've got this composition going on, right? So I first take X, apply transformation A, I get TA of X, and then I take that, plug it into transformation B, so to speak, and I get this final result. So again, we're doing sort of taking a little trip in our airplane from N space to M space, but we've got a little layover, right? We land over here in Atlanta or something, and we get on the next plane and hop over. It's much better if you can do what? A one-way flight, and that's what a composition does. It's going to go directly from N space to M space, and that transformation is what we're calling TB circle TA, which is sometimes written as T, transformation TBA. Now this is real important to understand that the order does matter here. And notice that we're doing transformation A first. You see how it appears here, and then transformation B back here. So be real careful. The common mistake is to get this order incorrect. Notice it's TA first, then TB, right? And notice though it's building to the left as we do that. And so that's real important to understand this notation here. The matrix for the standard matrix for transformation A, we'll just call matrix A. What size is that matrix? What size is that matrix? Do you remember how to determine the size of the standard matrix? It's going from N space to K space. So I have to multiply N tuples by it, right? So it has to have n columns, and the outputs are k tuples, therefore it has to have k rows. So it's k by n because it's going from n space to k space. All right, so if I'm going to multiply A by what, an n tuple, an n by 1 vector, right, it has to be that size. Transformation B's standard matrix we'll call B. What's the size there? What's the size there? Well, it's going to be m by k, because it takes k tuples, right, and outputs m tuples. Okay, so when we look at T BA of x, right, this transformation, again, this is TB of TA of x, that's the definition, right? And so how do we find TA of x? It's a times x, right? So how do I get here? I multiply by a. That's the, how do I fly? How do I take the flight? I multiply by the standard matrix A. And the standard matrix A here we said was what? K by n, and x is n by 1, which makes this whole thing what? A k by 1. As it has to be, it resides in k space, right? The image under transformation resides in k space, right? And so this is going to be TB of AX, right, which is a k tuple. And how do I do that? This is going to be B times AX. So how do I travel along this second flight, so to speak? I multiply by the standard matrix for transformation B, which is B. Now B, of course, again, is m by k, right, m by k. And we said AX, again, is k by 1. And so this whole thing is m by 1, right? It's an m tuple, as it should be. And then we can write this way as just BA times x. And this BA, then, this matrix is what size? Right? If I take a m by k times a k by n, I get a what? M by n. Right? So it's going from what? It's going from n space to m space. So it's a m by n matrix. And that indeed is our standard matrix for this composition TBA. Does the way we multiply matrices matter? Is order important? Yes. Remember, matrix multiplication not necessarily commutative. So it's real important that you understand this order. I'm doing A first and then B. A first and then B. Okay? And this is the way we write it. Now I can extend this concept. You know, imagine you ever had a flight where you had to do 2 connecting flights, right? You fly here, and then you fly here, and you fly another place, right? Well, we can have compositions of more than 2 functions. We can have 3 or transformations. We can have 3 or 4, right? But we can always form that one nonstop route. So, for example, what would it look like if I had a third transformation, say T sub C, composed with T sub B, composed with T sub A of x. So what do we mean by that? This is T sub B of, or T sub C of T sub B of T sub A of x. And we call this matrix transformation TCBA. What's its standard matrix? Just CBA. In that order. Notice again, this is what we do first, and this is what we do last. And it is important that you get that order out. That's a common mistake. If you change and multiply in the reverse order, that can be incorrect, because again, matrix multiplication is not necessarily commutative. Okay, so let's take a look. We're going to use results from the last lecture on the basic matrix transformations here, assuming that you've watched that. Write a standard matrix for the operator in 2 space obtained by a rotation of 90 degrees about the origin, followed by a dilation with factor 4. Okay, I'm going to call this transformation A. I'm going to call this transformation B. I'm doing A first and then B. So A is the standard matrix for transformation A. In the last video we saw how to do transformations. If you remember, it was cosine of theta, and theta is in this case 90 degrees, minus sine theta 90 degrees, and cosine, which I can evaluate. Cosine of 90 degrees being 0, sine of 90 degrees being 1, gives me this matrix here. We'll let matrix B be the standard matrix for transformation B, and that is, if you recall, we looked at dilations and contractions. They're just scalar multiples, so it's the factor, right, k, which is 4, down the main diagonal, zeros everywhere else. Okay, so that's how you do any dilation or contraction. Dilation is an expansion, right, because notice the value of k is bigger than 4. Right? So our standard matrix for TBA, right? Again, notice that it's not TAB because we're doing A first. Notice it's builds this way. So that is indeed just B times A. So it's matrix B times matrix A. Okay. Pretty easy to do that matrix multiplication. Row dot column is 0. Row dot column is negative 4. Row dot column is positive 4. Row dot column is 0. There's our standard matrix. So I can do a one-stop, flight by just multiplying by this matrix instead of multiplying by this one and then multiplying by this one. Now, let's look at the image of the vector x2, 0 under this operator. So what is t of 2, 0 equal to? Well, we multiply by this standard matrix that we just found. So one-stop flight, right? The vector in column vector form is 2, 0. And I multiply. 0 times 2 is 0. Negative 4 times 0 is 0. 4 times 2 is 8. 0 times 0 is 0. There it is. Or I can write it again back in comma delimited form. Let's see if this makes sense. Okay, we can look at this geometrically because we're in 2 space. So here's our xy axis, and we're starting with the vector 2, 0. Right. So we're starting right here. We'll just do the terminal point. Here's the vector, right? And what's the first thing we do? We did a rotation rather of 90 degrees about the origin. Okay, so if I go about the origin 90 degrees and rotate around, where do I end up at? Here's transformation A. Where do I end up at? At this point right here, which is what? That's 0, 2, right? 0, 2, right there. There's 2. Let's say 0, 2. Right? There's that point there. And then what do? We dilate by a factor of 4, right? Which is an expansion by a factor of 4. And we basically multiply the vector by 4. So if I multiply the vector by 4, I get what? 0, 8. Right? So transformation B is just going to shoot it straight out away, right? Transformation B to this point up here, which is the point what? 8, 0, 8, right? 0, 8, which is exactly what we got, right? That's so transformation A and transformation B. Now, I did say you do have to be careful about doing the correct order, right? What would be the A times B matrix? Well, that would be doing the dilation first, then the rotation, right? So think about that. What would TAB be, right? So now we're doing B first, the dilation first. Well, that's A times B. But if you take A times B in this case, if you change the order of these two and multiply them, guess what happens? I'll let you check and see. You get exactly the same. Exactly the same. And so we get TAB equals TBA. The standard matrices are the same. And in this case, we say that these operators, TAB and TBA, we say they commute. Is the word we use, they commute. Okay. And you can see this would be the case if I instead did the expansion first, right? Expanding by a factor of 4 away from the origin. Where would I go? From 2, 0, would I go out here to 8, 0? And then I do the rotation, I'm going to come around and be right there. Do you see that? So it's the same thing, always. And in this case, you'd be okay if you messed it up in terms of getting the standard matrix. But in general, that is not the case. And let me show you that in this next example. let's find the standard matrix for this operator. There's a reflection about the line y equals x. I'm going to call that transformation A. And then an orthogonal projection onto the y-axis. I'm going to call that transformation B. And then a reflection in the x-axis, transformation C. I don't know why I got two dots there. If you printed my notes out early in the semester, I think I added this to the problem. So just add that last little thing. So I've got three things going on. So I'm going to let matrix A be transformation A's standard matrix, and a reflection about the line y equals x. We did that one in the last video. Here's the standard matrix for it. B is the standard matrix for transformation B. That operator does a projection onto the y-axis. We also did that one. And then we'll let C be the standard matrix for transformation C. And a reflection in the x-axis, we did that one as well. And that's the standard matrix for that. So we did all these in the last video. If you're wondering how to get those, make sure you review that. So what I'm interested in is the standard matrix for transformation CBA. Notice again, A is the first thing we do, and C is the last thing we do. And so that's just C times B times A. C times B times A. So we'll just multiply this matrix C times B times A. Again, in that order. Okay. So I'll let you do the math there. If you do the math there, you get this as your standard matrix. Okay. Now, so there's the answer, right? So now I can do, instead of multiplying by this matrix and then this matrix and then this matrix, I just multiply this one matrix once, and we get the output to this composition of three transformations. Reflection about the line y equals x, orthogonal projection onto the y-axis, and then a reflection in the x-axis. What about, consider T, A, B, C, right? So now we're doing C first and A last, right? What's its standard matrix? It's going to be A times B times C. Well, that's the opposite order here, right? So 0, 1, 1, 0, 0, 0, 0, 1, and C is 1, 0, 0, negative 1. Well, in this case, this comes out to be 0, negative 1, 0, 0. So notice these two are, again, not equal to each other. Well, not again. The last one we saw, they were equal, right? The two operators commuted. But these two do not, right? These operators do not commute. And so this is real important when you're doing this. The order does matter. You got to be careful, because sometimes you're going to get different standard matrices. So make sure you get it in the correct order. Right? Whatever is done first will be to the far right, and then you'll build to the left of that as you continue to do the other operators. Okay? All right, so you're going to get plenty of practice with that in the homework for section 410. I'm going to practice those. We'll look at one last thing and sort of summarize a couple of things here. Some things we've already talked about, but just kind of put this all in perspective now as we're really ending chapter 4 here, and then I have one more thing to say with properties of matrix transformations. So the matrix transformation from n space to m space, first of all, is said to be one-to-one if the transformation maps distinct vectors or points in n space into distinct vectors in m space. Okay, so distinct or unique. Okay. Another way of saying TA is one-to-one is if we have the images under the transformation being equal, the corresponding pre-images, or the inputs, if you will, those vectors have to be equal. So I can't get the same image with two different vectors if it is one-to-one. Okay. This is something we already talked about again. This is a review of TA is a transformation from n space to m space. Right? Domain is n space, codomain m space. The set of all vectors in the domain that map into the zero vector in the codomain is called the kernel of the transformation, as denoted that way. So we've talked about the kernel. It's basically the same as the null space we're going to see as the matrix A, and we're going to talk about that. The set of all vectors in the domain, codomain, our M space is codomain, that are images under the transformation for some vector in the domain is called the range of the transformation. And it's real important. When we first started talking about domain and codomain, a lot of you were saying, I thought it was domain range. Well, here's where the range comes into play. The domain and the codomain, those are the vector spaces where these functions operate in, so to speak. That they have the input, if you will, in the domain, and then the output or the image is in the codomain. But the range then is a subset of the codomain. In fact, we're going to see it's a subspace of the codomain. Okay, so the range is the set of all outputs, right, that you get under the transformation. As long as there's a vector in the domain that maps to some vector in the codomain, then that vector in the codomain is in the range of the transformation. So, as I just said, the kernel of a transformation is just the same as the null space of A. The range of a transformation is the same as the column space of A. And if you remember that comes in from here. The column space of A is the same as what? Remember if the system AX equals B is consistent, we proved that B must be in the column space of A. Right? If AX equals B is consistent, then B is in the column space of A. Because why? Because AX can be written as what? A linear combination of the columns of A. AX can be written as a linear combination of the columns of A. So if AX equals B, then B can be written as a linear combination of the columns of A, which means it's the column space of A. Okay? And so what we're saying is we've been talking about a lot of these things, and this is sort of summarize these connections. So when we talk about them from three different viewpoints, we have a system of equations view, we have a matrix view, and we have a transformation view. So when we talk about a matrix view, the null space of a matrix A, that's the same as the solution space of AX equals 0. That's the system view. Right? That's what we mean by the null space, the solution space of AX equals 0. Set of all vectors X that satisfy that. Well, in the transformation view, that's just the kernel, a set of all values of X that get mapped to the 0 vector in the codomain. The column space of the matrix A, right, is the set of all B in M space such that AX equal B is consistent. Right? That's the system view, which is the same as the range of the transformation. Okay, so this is a summary. We've talked about a lot of these things, but this kind of brings it these very important viewpoints together. One more thing, a matrix transformation from n space to m space is called onto if the range of the transformation is equal to its codomain, which is m space. So in the fact that if the range of the transformation is equal to all of the codomain, then it is onto. Okay. Now, let's take a look at this important theorem. If A is what? Notice now it's what? Not m by n, not general, it's what? N by n. It's a square matrix. Yeah, square matrix. And T sub A from n space to n space, right? It's an operator in n space. Codomain and domain are the same. If that's the corresponding matrix operator, then the following are what? Equivalent. Equivalent. A is invertible. The kernel of the transformation is the 0 vector. Why is that? Why is that true? Remember, if A is invertible, AX equals 0, which is the solution space, right? Solution space of AX equals 0 is the null space of the matrix. Well, AX equals 0 has what? Only the trivial solution. So only the trivial solution. So null space is only the trivial solution, which is the 0 vector space. Right? The 0 vector space, 0 subspace, if you want to say it that way. The range of TA is all of n space. The range of TA is all of n space. And because why? Because the range is what? The range is the column space, and the column space, if A is invertible, is all of n space. Because if you remember those equivalent statements, if A is invertible, then what? The column vectors of A are linearly independent. They span n space, and therefore they are a basis for n space. Right? And so the column space of A is all of n space. And then TA is 1 to 1, and that's what we talked about up here. And that's true because it's 1 to 1 because, remember, if A is invertible, then there is exactly one solution to AX equal B for every, right, B in the n space in this case. Those are equivalent statements. And so if we go to the textbook again, right, we can pull up our wonderful equivalent statements list, right? Which, if you remember, in the last videos we were talking about previously, we got down, I think, to Q, but we've just said I added R, S, and T to the list. The kernel of the transformation is the 0 subspace. The range of the transformation is all of n space, and TA is 1 to 1. Those are the three we just added to the list. They are equivalent to A being invertible. And these are all connections that we need to know about, because again, like we said, when we're talking about, you know, linear independence, how are we doing that? We're sometimes looking at the determinant of the coefficient matrix. Is it not equal to 0? Right? And so on. So when we're looking at different things, we want to know certain facts. Sometimes it's easier to find a determinant or find something else a little bit easier, and we can obtain, right, the answer, because all these statements are either what? They're either all true or they're all false. And that's the beauty of this big equivalent statements theorem. Now, in closing, then, I want to talk about one last thing that's real simple, going back to matrix transformations themselves. If we have a matrix operator, right, that is 1 to 1, right, in other words, domain and codomain is the same, then we say if the matrix A, which is the standard matrix for the transformation, is invertible, then this matrix operator, right, TA with a superscript rather, -1, is called the inverse operator, or more simply, the inverse of the transformation. And quite simply, the standard matrix for that operator is going to be the inverse of the standard matrix for the operator T sub A, which is just A inverse. Okay, so it's just the idea of inverses from a matrix transformation view, the transformation view. So let's do these two examples and we'll be done. Show that the matrix operator defined by these equations is 1 to 1, and then find the standard matrix for the inverse transformation function. And then we're going to find the image under that transformation of W1, W2. Okay, so this system, remember, is represented as the vector W equals the standard matrix for the transformation T times X. Right? The W here is the vector W1, W2. X in this case is the vector what? X1, X2. So what's our transformation standard matrix? What's the standard matrix for this matrix operator going to be? It's just the coefficient matrix. Okay. There's my first thing. Find the standard matrix. Oops, no, that's not it. That's the standard matrix for T. Sorry. I want to find the standard matrix for T inverse here. How am I going to do that? First of all, let's show that this is 1 to 1, so that it indeed has such a thing. And how can we do that? Well, the easiest way is in that list of equivalent statements, find the determinant of the standard matrix, determinant of T, which is what? 5 times 3 minus -7 minus 2, which is 15 minus 14, which is 1. That's not equal to 0. And therefore, what do we know from our list of equivalent statements? This transformation TA is 1 to 1. Right. So there's the first part, prove that it's 1 to 1. And now I'll answer this question. What is the standard matrix for the inverse operator? Well, it's just the inverse of our standard matrix for operator. So this is just the inverse of this matrix. Okay. Now we can find this, with our calculator. We can crunch that out. There's also that little formula we gave before we can use, but I'll have you check and make sure that you know that this is the standard matrix for that. This is the standard matrix for that inverse operator. It's usually denoted again. Right, that's what we got. So there's that. And the last thing was to find the image of W1, W2 under this transformation. So what is the image of W1 comma W2 under this? So multiply by W1, W2 in column vector form. And I get 3 times W1 plus 7 times W2, right? Row dot column for the first entry. Second entry, row dot column, 2 W1 plus 5 W2. Right. And this is important because this is going to get us back to what? X1 comma X2, where we started from. And so notice we get this system of linear equations. X1 is 3W1 plus 7W2, and X2 is 2W1 plus 5W2. Okay. So this is the answer to what we were looking for, but I want to write it in this form, and this is important. So what we're saying is, sorry, I was off the screen there, but what we're saying is this is how we undo, in a sense, the transformation, right? So if we come back up here to the original, if I have X1 and X2 and I plug them in, I'm going to get W1 and W2. Well, if I take those values of W1, W2 and plug them in here, I'm going to get back to my original values for X1, X2. And I'll have you try, just try that. Just pick any two real numbers, X1 and X2, plug them into this, get your W1, W2, and then take those values, plug them in here, and get back your X1 and X2. Just go through the exercise. It's good. See how that works. That's how we undo operators. Now, last question, is the operator from 2 space that performs an orthogonal projection onto the y-axis 1 to 1? Well, before we do anything, let's just think about that. Is it 1 to 1? Right, an orthogonal projection onto the y-axis, right? So here's our y-axis here. If I have any point here, let's say at a height of y equal 2. Let's just say y equal 2 here. Okay, and let's put some x values down here. So if I'm at the point 2 comma 2, where does it go if it's projected orthogonally onto the y-axis, right? It goes where? Right to there, right to there, right to 0 comma 2. Well, what about negative 2 comma 2? Where does that go to? Also projects the same point. What about 3 comma 2? Where does that go? It projects there. What about negative 3 comma 2? It goes there. What about 10 comma 2? It goes there. What about everything is projecting onto that one point? Then clearly that is not 1 to 1. 1 to 1 says for every vector in the domain, there's a unique image in the codomain, and that's not unique. In fact, every point, every vector that's on this line y equal 2 will go to that same point. Okay? But we can see from, if you remember, the standard matrix for this, we did this in the last video again, is this. And what is the determinant of that standard matrix? Well, it's quite clearly going to be 0, right? See, a row of zeros or a column of zeros, we know the determinant is 0, which means that T is not 1-to-1. So we can quickly, obviously, compute the determinant of the standard matrix. If it's 0, that means all those statements we were looking at for an invertible matrix are false. And of course, being false, T is not 1-to-1. Okay? And we can't undo this transformation. It kind of makes sense, right? If all these points are mapping to 0, 2, how would I go back, right? 0, 2 going the other direction only gets mapped to one point. Which one does it go to? It doesn't work. Okay, we can't undo that. Okay, so that's all we're going to talk about as far as the properties. There's other things that could be said. Definitely go to page 277 in the book and take a look at those that list of equivalent properties, and it's theorem 4.10.2, but it's the big theorem. It's our list of equivalent statements so far, and you want to definitely go over that and think about those things and those relationships. Okay, so that ends all of chapter 4.